Hello everybody, this is lecture 3.2, all about linear functions. Ideally nothing new here, but helpful as we get into chapter 3. So we are in the student note packet, chapter 3, which is the buff yellow pages, and we are on page 3 of the student note packet. So page 3 of the student note packet, let's get started here. First thing we've been asked to do is determine whether the given function is linear or nonlinear, and we're given a table of values. So to determine whether a table of values is linear or nonlinear, we want to figure out what the slope, if there is one, is. So we're looking for the change in y over change in x, and we're looking to see if that's constant. If it is constant, we've got something linear. If it's not constant, we don't have a linear function. So if I'm looking at the changes in y here, from 4 to 1, we're subtracting 3. And then from 1 to -2, we're doing the same thing. -2 to -5, we're also subtracting 3. So all the way down on this first table, we're subtracting 3. The change in y is constant. So let's check the change in x, make sure that that is also constant. From -2 to -1, we're adding 1 again, adding 1, adding 1. So looks like the change in y and the change in x is constant. Therefore, we've got a function. This is linear. We need to find the equation when it is linear. So remember that the slope of a line we can define as change in y over change in x. We also call that rise over run. So the change in y here was -3. The change in x was +1. Our slope then is just -3. I'm going to use slope-intercept form to write the line here, the equation of the line. Y is equal to mx plus b is slope-intercept form. Remember, m is our slope and b is our y-intercept. So if we can take a look at this table and determine what the y-intercept is, that's probably the easiest way to go. The y-intercept occurs where the function or the line crosses the y-axis. That means x is 0 at that point. So we actually are given the y-intercept here with our table. When x is 0, y is -2. So our y-intercept is -2. Our final equation then is -3x minus 2. And this is linear. In the case of number 2, again, we're going to check to see if there is a slope, if the change in y over the change in x is constant. So from -26 to -4, we're adding 22. From -4 to +2, we're adding 6. And then we actually end up subtracting 4 and then subtracting 8. So this is not linear. The change in y over the change in x is not constant, so we'd have something else. In order to determine what this was, you might have to find the first difference, the second difference, the third difference, using those Algebra 2 skills from last year. So just as a side note, I've kind of worked that out over here. The third difference is what's constant here, which means this would be a cubic function. How about a problem like this, though? We're given a table of values, and we want to determine the same thing, whether or not this is linear. So let's take a look at the change in y and the change in x. So from 2 to 5, we're adding 3, and then 5 to 11, we're adding 6, and then 11 to 14, we're adding 3, and then 14 to 20, we're adding 6. So the way we have it right now, the change in y is not constant, it's not the same. But if we take a look at what's happening to the x values, we'll actually see something special occur. So from -8 to -6, we're adding 2. And then from -6 to -2, we're adding 3. And then we're back to adding 2. And then we're back to adding, -6 to -2 is adding 4. And then from 0 to 4, we're adding 4 again. So we see this change in x alternate, just like the change in y also alternates. So if we take a look at the slope of the line at this point here, right? Slope is change in y over change in x. That is 3/2. Now, if I take a look at the slope of the line here, change in y over change in x, we have 6/4, but 6/4 simplifies to 3/2. So this is indeed linear. I've just kind of thrown a trick out there where I've actually just skipped points that would be on the line. So we want to check to make sure that the change in y over change in x is constant everywhere. Even if the numbers don't exactly match up, it doesn't mean that the slopes don't simplify to be the same. For number 3, I would suggest pausing the video for just a minute and graphing f of x and g of x first. Part E is actually where it asks you to graph them, but it's easier if we actually refer back to the graphs of these. So I've got f of x, I've got g of x. I have graphed f of x with the red line, g of x with the blue line that you see on the screen, and we're asked to solve the following. So we're going to assume for parts A through D that we're not going to use the graphs, and then I'll refer back to the graphs after that. So we want to know where the function f of x is equal to 0. So in this case, I'm going to set f of x, that equation 4x minus 1, equal to 0, and I'm going to solve for x. In this case, x is equal to 1/4. If we actually look at that line on our graph, our function is equal to 0 when x is 1/4. That matches up with that point where we cross the x-axis there. So that's kind of what we're looking at graphically. All right, for part B, we are asked to solve where our function f of x is less than 0. So where is the red line? Under the x-axis, essentially. Where's our function? Where are the y values of our function less than 0, which means where is this red line? Under the x-axis. Now we cross the x-axis at x is equal to 1/4, and that red line is underneath the x-axis for all the values of x left of that 0. So we're going to write it like this: x is less than 1/4. For all of those values of x less than 1/4, our function f of x is less than 0. For part C, we're asked to figure out where f of x is equal to g of x. So I am going to do this algebraically first by setting these two equations equal to one another, and then I'm going to solve for x. So in order to do that, I'm going to move the x's to one side, the constants to the other. We end up with 6x is equal to 6. So x is equal to 1. Now that's only one part of our solution. We also need to figure out what the y value is there. So I'm going to take that value of 1 and I'm going to plug it into either the right or left side, or f of x or g of x, in order to find y. So when x is 1, y is 4 minus 1, which is 3. So our solution for where f of x is equal to g of x is the ordered pair 1, 3. And if we look at the graph, where the two lines intersect, that's the point 1, 3. That's where we see the functions equal to one another. For part D, we're asked to figure out where f of x is greater than or equal to g of x. So we want to figure out where the red line has greater y values than the blue line. So if we're looking graphically at this, we are actually looking literally for where the red line is higher than the blue line. If we want to solve this algebraically, all we're going to do is see where f of x, which is 4x minus 1, is greater than or equal to negative 2x plus 5. So I'm going to do this algebraically, and then we'll take a look at how that looks on the graph. So again, I'm going to move all the x's to one side, everything else to the other. I get 6x is greater than or equal to 6, and then to get x by itself, we'll divide. So in this case, x is greater than or equal to 1. So for all the values of x greater than or equal to 1, that's where f of x is greater than or equal to g of x. So if I take a look, x is equal to 1 at the place where these two lines intersect. So it looks like this. I'm just going to drop a vertical line down. And our solution tells us that we're only looking at the values of x greater than or equal to this point. So we don't care about anything to the left of that vertical line. And so if I were to cover up everything to the left of that vertical line, the point at which our functions intersect, we see that's where the red line is taller than the blue line. That's where f of x has y values or function values that are actually greater than g of x. All right, so then in the process of working through this, we've already kind of answered part E. We've got the graphs, we've labeled the points that represent the solution to these two equations equal to one another. So for number 4 and 5, I would recommend actually pausing the video and then working through A, B, C, D, E, and F, and then coming back at the end, I'll have the answers put up there. So the answers for 4 are here. Part A, where's our function equal to 50? We're looking at where the y value of the function is 50. So the x value that yields a y value of 50 is 40. X is equal to 40 for part A. Part B then, where's our function equal to 80? So you're looking at the ordered pairs with a y value of 80, and then we're giving x as our solution. So x is equal to 88 is part B. Part C, where's our function equal to 0 at negative 40? Part D, where's our function greater than 50? So our function is greater than 50 everywhere to the right of x is equal to 40. So for x greater than 40, our function is greater than 50. And then part E for where is f of x less than or equal to 80? Well, when x is 88, our function is equal to 80. So for all the values of x that are less than or equal to 88, our function is less than or equal to 80. And then the last one, f, is the trickiest one here. Where's our function between 0 and 80? Our function is between 0 and 80 on the interval negative 40 to 88. And we don't include negative 40 or 88 in the solution there because we don't want to know where our function is equal to 0 or equal to 80, just strictly between those two values. Same thing for number 5. Go ahead and pause the video and come back after you've got those solutions to check. First part, we want to solve the equation, where is f of x equal to g of x? Not a whole lot to do when you've got the graph there. The solution here is negative 4 for x. Negative 4, 6, that ordered pair is actually where the two functions intersect. To solve the equality, where is f of x greater than g of x? We're taking a look at where the function f of x is literally above on the graph the function g of x. So again, I'm going to drop a vertical line at the point where these two things intersect, and we're looking for where f of x is taller than g of x, and that happens everywhere to the left of the line where they intersect. So we are going to write the solution there as all the values of x that are less than negative 4 as our solution for where f of x is greater than g of x. Number 6 is the trickiest one on the page. So for part A, we want to know where f of x is equal to g of x. Well, g of x is the bottom horizontal line there, and f of x is that transversal. So where are they equal to one another when x is equal to negative 6? It's that point, negative 6, negative 5, where they intersect. Part B is actually the harder of the two options. So we want to know where the function g of x is less than or equal to f of x, which is less than h of x. So I am going to color code these lines, and then we're going to go from there. I'm going to color code g of x with a green line, and then I'm going to color code f of x with purple, and then h of x I'll keep blue. And the question is this: we're looking for where the function values, the y values of g of x, are less than f of x, which is less than h of x. So if we're actually looking graphically, we're looking for the place on the graph where the blue line is above the purple line, which is above the green line. And I know that's not mathematical, but that's kind of a good way to visualize. So the place on our graph where the blue line is above the purple line, which is above the green line. So if you take your pencil and you make your pencil vertical, and then you place your pencil down on your paper and you move it left to right, we're looking for the places at which that order of colors, blue, purple, green, are true. So I'm going to use a vertical line as my pencil here, and I'll do that in orange. And maybe you can see what I'm looking for. So if I drop my pencil right here, to the left of that, we have blue, green, and purple is the order from top to bottom. Blue, green, and purple. So this doesn't get included in our solution. That's not the interval that we're looking for. So then I'm going to keep moving my pencil, and I'm going to take a look right between those two parallel vertical lines. And between those two parallel vertical lines, what do we have? Well, the order is blue, purple, and then green. And that's exactly what we're looking for. We're looking for blue, purple, and green. So the interval between those two parallel vertical lines, which is where I paused my pencil, is going to be the solution that we're looking for. So we're looking at the x-axis between those two parallel lines. So that's going to look like that. Negative 6 on the lower end, that's our lower bound. And then our upper bound along the x-axis is 5. So our lower bound, negative 6, upper bound is 5. X is going to be between those. Now, I'm going to write my final answer like this. X must be greater than or equal to negative 6, but less than 5. We can be greater than or equal to negative 6 because f of x could be equal to g of x, but we cannot use an equals with the 5 because f of x needs to strictly be less than h of x, and at 5, f of x and h of x are equal to one another. One more thing to note, if I look at the region of my graph to the right of the far vertical line, the order of colors there is purple, blue, and green, which is why I know that that's not the interval I'm looking for either. So for the back side of this paper, 7, 8, and 9, I think that you could probably do these on your own and maybe just fast forward the video after you've got a solution for each of them to check your answers. But I'm going to walk through all of them now. So number 7, we've got this function here, represents the tax bill of a single person whose adjusted income is between $7,825 and $31,850 per year. So, and this is quite outdated, 2007 here. We're asked to do the following. We want to know what the domain of this linear function is. That's part A. So the domain, what can we plug in for x? Now, x, if we were to go back to this equation, right, x represents our income for a year. And because we're told we've got a lower and an upper bound on income, our domain is restricted to the values between $7,825 and $31,850. Now, we are told we include those values, so x can equal both of those. So our domain here is x is greater than or equal to 7,825, less than or equal to 31,850. Part B asks us what a single person's tax bill is if their income is $18,000 for the year. So all we're going to do is take a calculator and we're going to plug in 18,000 as x in this equation. And then we're going to solve. So when I plug in 18,000 here, we should get something like $2,308.75. The only thing you have to really worry about here is that you're rounding correctly. We're representing money, so it's 2 decimal places. Okay, so somebody that makes $18,000 a year owes $2,300 in taxes. What variable is independent and which is dependent? Well, the independent variable is what we plug into the function. So our independent variable here is x. Which stands for your yearly income or annual income. The dependent variable that's our T of x. That's our tax bill. Our tax bill depends on how much money we make a year. All right, graph the linear function over that domain specified. And now you only need 2 points to graph a line. So I'm going to find 2 points. I'm going to find that lower bound and the upper bound point, and I'm just going to plot both of those and then draw a line between the two. So I'm going to plug in my lower bound, 7,825. When I type that into a calculator and calculate, I get $782.50, and then I'm going to do the same thing for my upper bound on my domain. So $31,850 gives us a tax bill that is $4,386.25. So I'm going to plot the points here, 7,825, 782.5, and 31,850, 4,386.25. So I'm going to plot both of those points on my graph. I'm going to scale it. I'll be right back. All right, so the graph looks something like this. I just scaled kind of roughly and then plotted those 2 points and drew a line between them. So that represents our linear function over only that domain specified. We don't want to have arrows to the left and right because we're restricted within those income values. So part E is the most complicated. It just requires a little bit more algebra. So I'm actually going to erase this page so I can show some more work. And part E tells us this. We have somebody's tax bill. We're told that somebody pays $3,358.75 as their tax bill, but we want to know what their annual income is. So we need to solve for X. So there's different ways you guys could go about doing this. You could distribute that 0.15 into the parentheses first and then combine like terms and get X by itself. I am going to do this a slightly different way. I'm going to subtract 782.5 from both sides first. That gives us 2,576.25 equal to all of this. And then instead of distributing that 0.15, I'm just going to divide both sides by 0.15 and get rid of it. That is going to give me 17,175 on the left, and then x minus 7,825 on the right. And then to get x by itself, just add 7,825, and we get $25,000 is equal to x. So somebody's annual income, somebody who makes $25,000 a year will pay $3,358.75 as their tax bill. All right, so for number 8, we've got a company, and we're told the point at which a company's profits equal 0 is called their break-even point. So R represents the company's revenue, and C is going to represent the costs. And then X is the number of units produced and sold each day. So imagine, well, I don't know, we're making like cell phones. And so X is going to represent the number of cell phones that we sell. R is our revenue, and C is the cost. How much does it cost us to make these phones? Part A asks us to find the break-even point. So where is our revenue equal to our cost? All we're going to do is set the revenue equation equal to the cost equation, and we're given both of those below, and we're just going to solve for X. So when you go about solving for X, we should be getting 5,000 units. I'm going to let you guys do the algebra on that one. Okay, so to break even, that means make exactly what it cost us to create the phones. We need to sell 5,000 phones. So then part B asks us to figure out the values of X such that our revenue is greater than our cost. This is going to represent the number of phones we need to sell in order to earn a profit. So we know that if we sell 5,000 phones, we break even. Our cost meets our revenue, which means that in order to create a profit, we have to sell more than 5,000 phones. Now, the way we're going to write this is instead of X is greater than 5,000, I'm going to express this as X must be greater than or equal to 5,001. Okay, the reason I'm going to write it this way and not this way, let me do this in a different color, is because this implies that you could have 5,000.5 to satisfy where our revenue is greater than our cost. But we're selling units of something, and we're not going to sell a half a phone or a half of anything. So we're going to represent that final solution as X is greater than or equal to 5,001 units. All right, last example, number 9. We've got the situation. A truck rental company rents a truck for one day by charging initially $29 plus 7 cents a mile. We want to write a function that relates the cost in dollars of renting the truck to the numbers of miles given. So I'm going to call our function cost C of X, and that is equal to 7 cents for every mile that we drive plus the initial cost of $29 to rent. So that is part A. Part B then asks us what is the cost of renting a truck if it is driven 110 miles versus 230 miles. So I'm just going to plug in 110 to this equation for X, and we get $36.70. And then for 230 miles, I'm just plugging in 230 for X, and we get $45.10. That is it for 3-1. Ideally, review for everybody. Get started on your homework. Email me if you've got questions.